Hello everyone, and back to proof. Before we get going on today's proof, you might have heard, with the world in lockdown, nobody can get out. So a lot of people have been making bread. It's the ongoing thing. I don't know if you've been following. I don't know if you're making bread at home. Who's making bread at home? I know a lot of people around the world. A lot of my friends never made bread before. All they talk about on social media is making bread, making bread. That's their son life. So what did the bread dough say to the baker? That's what we want to know. What did the bread dough say to the baker? Okay, so we're going to continue on proof. Today we're going to talk mostly about even odd proofs and counterexamples. So first off, let's say we wanted to prove that the sum of any three consecutive integers is a multiple of 3. First off, we need to remember what's an integer. We did this in module 1, right? Integers are the positive and negative whole numbers. So -3, -2, 1, 0, 5, 17, those are all integers, okay? Fractions, 1/2, decimals, 0.3 recurring are not integers. Consecutive means one after the other. So consecutive integers would be things like 1, 2, 3. They are consecutive integers. Or -7, -6, -5 are consecutive integers. So Bart here is showing off his proof skills. So his proof is 5, 6, 7. Those are consecutive integers. If we add them up, we get 18. That's divisible by 3. So he's proved it's true. What is wrong with his proof? Okay, well, when we prove things, we have to prove it's true for everything. He's just done one example. How do we know that that one example is going to work for everything, right? What if we try 11, 12, 13? What if we try -27, -26, -25? Will they be divisible by 3? So this is what we're going to talk about in proof. We won't do this proof today, right? But this is sort of what we're leading up to. How can we prove a statement so it's going to be true for any number that I might want to go ahead and try? Okay, here's an example of a sort of a famous proof. Euler, one of the greatest mathematicians of all time, he noticed that this formula gave prime numbers for many positive integers n. So we might wonder, is this true for all positive integers n, where n squared minus n plus 41? So again, we might just start trying some things like, right, so what about when n is 1, right? We can't use 0, we're saying positive integers. When n is 1, 1 squared is 1, minus 1 is 0, plus 41 is 41. That's prime. What about when n is 2? 2 squared is 4, minus 2 is 2, plus 41 is 43. That's prime. What about 3? 9 minus 3 is 6, plus 41 is 40. That's prime. What about 4? That's prime. What about 5? How long do we need to keep going? Right? How do we know this is true for all numbers? Right? Can we try all numbers? It would take us forever. So how can we prove something like this? Or how can we prove that it's not true? Okay, so I'll tell you this is not true for all positive integers then. We're going to pause the video. I want you to have a ponder. Can you find a number n such that this statement is not true? Because this is not true for all n. So give it a think. Find a number. There is more than one number that makes this statement not true. Okay, so one number, again, sometimes these things it could be a lot of trial and error, or sometimes we need to think about things a little bit. What if n is 41? Think for a second, why would I choose 41? If n is 41, there might be other ones, right? And there are other ones, but I don't want to do a lot of thought. I don't want to try 5, 6, 7, 8, 9, 10, 11. 41 squared minus 41, that's still going to be a multiple of 41, isn't it? Right? 41 times 41 minus 41 is a multiple, and then plus 41. Well, obviously that's not prime, is it? Because it has a factor of 41. Because minus 41 plus 41 is 0, 41 squared. I know that's not prime. Okay, so sometimes we do these proofs, we need to think. This is what would be called a counterexample, right? I've proved that it's not true using one specific. That's all I need is one example to prove something is not true. To prove it's true, that's a little bit harder. Okay, so let's look at another counterexample here. Prime numbers are always odd. Can you find a counterexample? So a counterexample is something we use to prove that something is not true. Okay, and again, to prove it's not true, all we need is one example. If there's one number, prime numbers are always odd, well, that's pretty straightforward, isn't it? 2. 2 is prime, and 2 is not always odd. And as a matter of fact, in this case, that is the only counterexample. Sometimes there might be more than one. In this case, that is the only counterexample that shows that this is not true. So again, counterexamples don't prove things, but they can prove things are not true. Okay, what about another counterexample for this? The square root of a number is always smaller than the number itself. When you get things like this, if you're not sure, just start trying some examples to see how it works, okay? What about 9? The square root of 9 is 3. That's smaller. What about 4? The square root of 4 is 2. That's smaller. What about 1? The square root of 1 is 1. That's not smaller, is it? So there's one counterexample I found, and that's all we need for something like this. But just to explore this a little bit more, what are some other counterexamples we can find? Or is 1 the only one? Okay, now notice they said number here, right? They didn't say integer, right? What's the square root of a half? Flashback to our surds. All right, flashback to our surds. Or, I'm sorry, not square root of a half. I'm thinking about something else. Square root of a quarter. What's the square root of a quarter? All right, think back to our surds. This is the square root of 1 over the square root of 4, which is 1 over 2. Is 1/2 smaller than 1/4? No, it's bigger. So if there's two counterexamples, and we can find a lot more. Basically, any fraction, if you take the square root, the answer is going to be bigger. Okay, so we found one example where it was the same, and we found another example where all we needed was 1 to answer this question. But just to explore the topic a little bit more, we went ahead and found 2. Okay, can you find counterexamples for this statement? If p is prime, then p plus 2 is prime. Okay, well, there's an easy one to start with, right? What about if p is 2? That's prime. P plus 2 equals 4. That's not prime. I found a counterexample. So if p is prime, then p plus 2 is prime is not always true. Can I find some more? Sure. What about if p is 19? 19 is prime. What's p plus 2? Is 21. Is 21 prime? No. Right? So there's lots of counterexamples that we could find to prove that the statement is not true. If p is prime, then p plus 2 is prime is not true. Are there some that works? Yeah, sure, there are ones that work, right? If p is 3, p plus 2 is 5, that works, right? If p is 11, p plus 2 is 13, that works. So there's lots of examples that work, but there's also lots of examples that don't work. Okay, let's make it a little more interesting. Counterexamples for this statement. 2n squared plus 11 is prime for all integer values of n. Again, you might just start trying some things to see if it works. Right? Well, what about with n is 1? Well, I get 2 plus 11 is 13. That's prime. What about when n is 2? 2 squared is 4 times 2 is 8, plus 11 is 19. That's true. What about when n is 3? 3 squared is 9 times 2 is 18, plus 11 is 29. That's true. Oh, this might keep going for a while. Again, you can keep going, right? What about 4? When n is 4, 4 squared is 16 times 2 is 32, plus 11 is 43. That's prime. So you start wondering, how long am I going to keep going? Okay, again, think about it. This is similar to that Euler one, right? What am I going to try right away to save myself some time? 11. Because 2 times 11 squared, right? So 11 squared is a multiple of 11, times 2 is a multiple of 11, plus 11 is a multiple of 11. So without even working out what this expression is, I know that this is not prime. This number, if I go ahead and calculate it, 2 times 121 plus 11, right? 121, that's 242 plus 11 is 253. And I know that that's a multiple of 11. So it's not prime. So there's a counterexample. Are there more? Sure, there's more. Sometimes we need to be smart, clever, creative in how we go ahead and find our counterexamples. Don't always just blindly start crunching numbers. Okay, the next type of proof we're going to look at are even odd proofs. Okay, before we do, let's just do a quick review. Some basic arithmetic, right? Even plus even gives me an even number, doesn't it? Okay, and even plus odd gives me an odd. Okay, odd plus odd is even. Again, just try two numbers and see what it is. And we've already done odd plus even. Okay, so that's adding. What about when I multiply? right? Well, even times even, 2 times 4 is 8, that's even. Okay, even times odd, 3 times 2 is 6, 3 times 4 is 12 is even, and odd times odd is odd, isn't it? Okay, so again, this is, some facts we learned about arithmetic way back in primary school, but we can use these to prove some things. So I want to show is usually another word for prove, that for any integer n is n squared plus n is 8. All right, it says for any integer n. You can't just stick a couple numbers in and say it's true. Unless you're going to stick every integer n, and the integer is never n, so there's no way you could do that. You need to find another way to prove this. So n squared. So again, we need to break this proof down. Any integer n. N could either be even or odd. Okay, so let's write it. Let's say if n is even. Okay, what happens? Well, n squared is even times even, and then plus an even. And even times even is even, plus even is even, right? Okay, or n could be odd. There's only two choices for integers. They're either even or they're odd. So if n is odd, then I would have n squared is odd times odd, and then plus an odd. And I know odd times odd is odd, plus an odd is even. So this is my proof, right? You don't have to write down what's on the right-hand side. We just we'll take that as accepted fact. Your working out is what is on the left-hand side. That is your working out, right? You need to take in all cases, and all cases are n is even or n is odd. Let's look at another even odd proof. Prove that n times n minus 1 plus 1 is odd for all integers n. Okay, so again, all integers n, and I want to prove something is odd. So my choices are n could be either even, it doesn't matter where you start, n could be even, or n could be odd. Okay, if n is even, then what do I have? I have even times even minus 1 is odd, plus 1, okay, and even times odd is even, plus 1 is odd. So it's true if n is even. Any even number we pick. And what about if n is odd? Okay, well I have odd, and an odd minus 1 is even. Inside the bracket, odd minus 1 is even, plus 1. Well, an odd times an even, right, is even, plus 1, and any even number plus 1 is going to be odd. So I've proved it. This is the working out. You've got to lay it out like this. You cannot just put some numbers in. You could put 100 numbers in. That doesn't prove it's true for all integers. Okay, a nice challenging problem here using the facts about even and odds. How many different positive integers n are there for which n and n squared plus 3 are both prime numbers? I'm going to pause the video and I want you to think what the answer is. Okay, so what did you get? And let's look at how we could do that. All right, we could just start sticking numbers in. That might take a while. Let's think about this and use the power of these even odd proofs. Okay, so there's two choices, right? N and n squared plus 3 are both prime numbers. Okay, well n could be even, couldn't it? The only way it could be even is if n is 2. Okay, if n is 2, that's prime. Okay, and n squared plus 3 is going to be 7. Those are both prime. We found one that works. Okay, we found at least one answer. So we know it can't be A because we found at least one answer. Can n be any other even numbers? No, because there's no other even prime numbers and n has to be prime. So the next thing is, what about if n is odd? Okay, now notice I'm not going to start choosing specific numbers because there's a lot of odd prime numbers, right? N could be 3, 5, 7, 11, 13, all these different things. Okay, so rather than try things, if n is odd, what's n squared plus 3? Well, n squared is odd times odd plus 3. Odd times odd is odd, plus 3 is even, isn't it? Okay, well, they have to both be prime number. How many even prime numbers are there? 2. But whatever number I start with for odd, if I started with n was 1, ultimately I'm going to have to add 3 to it, which is going to be bigger than 2. So can there be any answers when n starts at odd, whether n is 1? We can try 1, right? Well, n equals 1 is not prime, so it can't be 1. We could try 3. 3 squared is 9 plus 3 is 12. That's even. That's not prime. If n is 5, 5 squared is 25 plus 3 is 28. That's not prime. So you can see that any odd prime number I stick in for n squared plus 3 is not going to be prime. So what is my answer? My answer is B. There is only one positive integer, and that's when n is 2. And how we get there by using the power of evens and odds. Okay, let's look at another one. Prove that 2n plus 1 is odd for all integers. This is a really common expression that we're going to see a lot in some of our upcoming videos, that 2n plus 1 is odd for all integers n. So how can we go about doing this? Again, okay, what about if n is even? Well, 2 times even is even plus 1 is odd. And if n is odd, well, 2 times odd, 2 times an odd is even, plus 1 is odd. So I've proved that 2n plus 1 is odd for all integers n. Any even number, any odd number I choose. Okay, another one. Prove that n cubed minus n is always even for all integers n. Okay, well, we can go about it the same way. What about if n is even? I would have even times even times even minus even. Well, even times even is even, times even is even, minus even is even. What about if n is odd? Well, I have odd times odd times odd, right? It's cubed minus odd. Well, odd times odd is odd, times odd is odd, and odd minus odd is odd, right? Is even, I'm sorry. 11 minus 3 is 8, right? Is even. Okay, I hope it's even. And as it turns out, it is even. Okay, so these are some nice, good examples of how we can use the powers of even and odd to prove some statements. Okay, let's look at a counterexample question. What is the smallest positive counterexample for the statement that p is prime, then p squared plus p plus 1 is prime? Okay, again, if you're not sure, if you're not sure what the statement means, how to go about it, then start with some examples, right? If p is prime, so let's start with the smallest p number, which is 2. That's the smallest prime number. Then p squared, that's 2 squared, plus 2 plus 1, that's 4 plus 2 is 6 plus 1 is 7, that's prime. Okay, that works. What about when p is 3? Well, I have 3 squared plus 3 plus 1. 3 squared is 9, plus 3 is 12, plus 1 is 13. Okay, that's prime. What about if p is 5? Okay, then I would have 5 squared plus 5 plus 1. 5 squared is 25, plus 5 is 30, plus 1 is 31. Okay, p is 7. I would have 7 squared plus 7 plus 1. 7 squared is 49, plus 1 is 56, plus 1 is 57. And I know that's divisible by 3, isn't it? Okay, so it looks like that 7 is the smallest positive counterexample for the statement that p is prime. Again, p is prime, so we're only starting with prime numbers. Started with the smallest ones and went ahead and worked my way up there. In this case, since they're looking for the smallest one, you're probably all right, and I don't really see a way that you can really break this down. There's no real way to use the even odds ones on this, because if you try to do a proof, this will always be odd, this expression, right? P squared plus p plus 1 is always going to be odd, no matter what p is. So that's not really going to help you on this one. This one, you might just need to try some different examples. Okay, last question for the video. Which of the following values of n is a counterexample to the statement, if n is a prime number, then exactly one of n minus 2 and n plus 2 is prime? We're going to pause the video. I want you to go ahead and see if you can figure out, using everything we've just talked about, what the answer is going to be for this one. Okay, so if n is a prime number, well, right away I look at this, I see 21, that's not a prime number, so the answer can't be C. I can cross that one off right away. The other four answers are prime numbers. So what's the best way? Really just check them, okay? So if n is 11, n minus 2 is 9, n plus 2 is 13. Is one of those prime? Yes, one of those prime. That's true. So that's not a counterexample. That proves it's true. I'm looking for something that proves it's not true. Okay, what about when n is 19? N minus 2 is 17. N plus 2 is 21. Is that a counterexample? No, because one of those is prime and one of those is not prime. That's what my statement says. If n is prime, then exactly one is prime. Okay, what about 29? Well, 29 minus 2 is 27. 29 plus 2 is 31. Well, one of those is prime. 31 is prime, 27 is not prime. So it looks like, right, again, we saved some time by not even trying C. It looks like E is going to be it. We have to double check it. 37 minus 2 is 35. 37 plus 2 is 39. Neither one of those is prime, right? 35 divides by 5. 39 divides by 3, as well as other things. So that is a counterexample. So which of the following? So 37 is a counterexample. That proves that that statement is not true. Could there be other ones? Yes, but out of those choices given, that is our counterexample. Okay, so that takes care of even odds and some basic counterexamples. In light of the lockdown and the bread baking that's gone crazy around the world, what did the bread dough say to the baker? It's nice to be needed.